A warm good morning to one and all present here. Dear participants, feedback link will be posted at the end of the session and kindly post your queries in the chat box. Mathematics is not about numbers, equations, computations, or algorithms. It's about understanding. The power of prayer is like turning on a light as it illuminates God's purpose for our lives. There is no greater connection to knowing His will other than words. Let us begin today's session with Tamil Thai Valthu, followed by college prayer song.
அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் திகழ்ந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
Now, I welcome Dr. B. Abhirami, Assistant Professor, PG and Research Department of Mathematics, to render welcome address.
Mathematics knows no races or geographic boundaries. For mathematics, the cultural world is one country by David Hilbert. A very good morning to one and all present in this virtual webinar. It gives me immense pleasure to extend warm welcome on behalf of PG and Research Department of Mathematics, conducting one-day national webinar on uniform convergence by the resource person, Dr. P.S. Srinivasan. He is an Associate Professor, Department of Mathematics, Bhayadasan University, Tiruchirappalli, and also resource person for ICT program past 2 decades. We welcome you, sir. I also welcome our beloved HOD, Professor R. Venkatramanan, for his continued support to conduct a series of national webinar. I also welcome all the teaching fraternities, research scholars, and students present in today's national webinar. Thank you.
Thank you. Now I welcome Mr. R. Rajshekhar, Assistant Professor, PG and Research Department of Mathematics, D.G.VAISHNAV College, to introduce our resource person, Dr. P.S. Srinivasan.
Good morning to one and all present here. It's my great pleasure to introduce our resource person, Dr. P.S. Srinivasan, Assistant Professor, Department of Mathematics, Bharadasan University, Tiruchirappalli. He did his PG from IIT Bombay and PhD from IIT Madras, postdoctoral from University of Hyderabad. He has more than 13 years of teaching experience and research experience. His area of research is fixed point theory and discrete dynamical system. He successfully guided 30 MPhil students and presently two of them pursuing PhD. He published 7 international and 2 national journals. He has also organized 2 workshops and delivered 50 invited talks. He is also membership in Ramanujam Mathematical Society. He is a resource person for the past 15 years in MTTS, Mathematical Training Talent Search Program. With this brief introduction, I welcome you, sir. Now I hand over the session to you, sir.
Good morning. Good morning to one and all present here for this nice August morning. At the outset, first I thank D.G.VAISHNAV College chairpersons, and in fact I should thank each one of them for giving me an opportunity to come in front of you and have a and share my experience. Yeah. So as of course, as the time progresses, it's a very limited time, and the topic whatever I have taken is clearly a BSc level topic, right? Nowadays it's being done in BSc, but of course this forms a very core part of analysis topic, and it's very important in later period. Let's talk about the word uniform convergence, and of course as the professor indicated in the introduction, that it's not mere manipulation. What we have to learn is the idea. Okay. So before going to uniform convergence and all, I'm going to start with something which is very quite natural. Okay. Let's take a standard example, whatever we have in R. Okay, some logical point we should understand first. See, I'm going to explain the word uniform first. Okay, for that we should have some idea what is uniform and what is not so uniform. All of us understand what's a uniform, right? A plain English term, most of us understand. Policemen wear a uniform. All the policemen wear a common uniform, right? And army people wear a different kind of uniform, but all of them wear. Air Force wear a different uniform. School, depending on school, each school has a uniform. Okay. Yeah. So we understand the meaning of the word uniform, and nowadays uniformity is sorted, right? Yeah. So let's explain what we mathematically mean by the term uniform. Same thing only, but let's understand what it is, and we'll also understand how difficult it is to sort for. Okay. Yeah, it's a very tough condition. Uniformity is a tough condition because it's not quite natural. Okay, but still we sort it for our convenience because it has a very nice structure. If we have uniformity, okay, we can understand what is going to we'll see what are all the things we have. So first I'm going to start with some logical statement where I want all of you should understand. So given X in R, all of us know this. There exists Y in R, but you may not know the fashion which I am writing. Okay. Let's say most of the readers seeing this would have immediately identified. Sir, what is this? This is the additive inverse property. Okay. Most of you would have understood what it is. Given a real number X, for example, if I give X equal to 2, then I'll have a Y. What is that Y? That Y is called the additive inverse of X. Because Y being unique, we call it as actually -2. Okay. Those things algebra people know. Yeah. If you have a little concentrated thing on algebra, you know. But let's understand. If I have X equal to 2, I'll have Y depending on X. Is that understood? So Y changes according to X. Okay. Now let's look at another statement what we have. Yeah, if I give X equal to -√2, then what is going to be Y? Y is plus √2. Yeah, that's how we denote additive inverse. Actually, there is nothing much what I'm trying to tell. But anyway, you understand in a very loose fashion. So depending on x, my y changes. That's what you have to understand here. But let's take the identity property. What is the additive identity? Or in fact, we can take anything. Let's take additive identity. 0 is an element of R with the following property. What is the property? For all x in R, x plus 0 equal to x. There is a common fellow, what all we know in the real line. Okay, most of us would draw real line, right? 0 is there. What is the property of 0? If I add 0 with any x, okay, the identity of x does not get changed. It will same as x. Okay. Yeah. So here, there is a common fellow. Yeah. Such that for all x, this is happening. Okay. These two things you should understand. Okay. Right. So let's understand the structure of this statement, in fact. Okay. Usually students, what they do is they try to interchange this and write. Okay. So there is, suppose if I write like this, there exists, suppose if I write as there exists, what is happening? Oh, it has gone to somewhere. There exists y in R such that for all x in R, suppose if I write like this, x plus y equal to 0. Then what can I say about this statement S2? Call this as statement S1. Okay. Here the meaning completely changes. That's what people will say. Yeah, no, some of the students will immediately say, sir, both are same statements, sir. Just you have changed the order. Okay. Of course, this is a true statement, but this is a wrong statement. This is a wrong statement. Why it is wrong? I cannot find y like this. But in mathematics, I don't say like that. Therefore, I go for the negation. What is the negation? Given y in R, I will be able to say I can find an x in R with what property? X plus y not equal to 0. This is the negation of that. Okay. It will take time for you to understand. Okay. Take a time. Assume something like this. Okay. Suppose if I say, even here now, there is a participant, okay, of this seminar who comes from Punjab. If I say, if it is false, what do I mean? There is no participant from Punjab. That's what our English understanding is. Correct. But we don't say that in mathematics. We still go deeper. Deeper means we want a proof. How do I prove there is no participant from Punjab? I have to check each and every participant's address. Right? So that's what we are doing. Given any participant, y, whatever I wrote in the bracket, that property was false. That means, yeah. Again, go and understand the meaning. Okay. So it takes time for you to understand. Okay. This statement is something like this. Suppose nowadays it's a season of oranges, no? A shopkeeper says, every orange in this basket is ripe. If it is false, means what? Not all oranges. See, some students will say that all oranges are not. No. That's not the thing. Every orange is ripe. Means if it is false, means what? I can find at least one from the same basket, okay, which is not ripe. Yeah, so you have to understand the point. Okay, this is the negation. That's why whenever we write quantifiers as such. So this is the negation. After having understood, I can prove this, right? Start with the y in R. Can you give an x? So what is the x I want? X plus y not equal to 0. Therefore, y should not be equal to minus x. That's all. There are a lot of choices. Okay, because R is plenty. It's an infinite chess set. Okay, I have to choose an x. Or in other words, I want an x such that x not equal to minus y. So just say choose x such that x in R such that x not equal to minus y. Or in other words, choose x in R difference singleton minus y. And this set is non-empty. Because it's infinite. If I remove one element, again, still it will be infinite. Plenty of elements are available. Okay, one should go by that. Don't say 2 is there, 3. I don't know about why. We should know how to argue. Okay. Yeah. So that's how things work. Right? Okay. And one thing, you should not change the quantifier. Okay. So that's the point. Okay. Let's now talk of sequences. Okay. Yeah, first one should understand. Most of you know, and I pre-assume now. What do I mean by saying AN, a sequence of real numbers? Let's now work only with real numbers. What do I mean by saying sequence of real numbers converge? AN is a sequence of real numbers. I want to say AN converges to A. A is also a real number. Okay, let AN, suppose, or if AN is a sequence of real numbers and A in R, what is the meaning of AN converges to A? How do you explain this to a layman? Say, for example, a shopkeeper. Okay. The idea is this, because usually if there are audience, I can ask them. But anyway, the idea is this. I will simply say the idea. Here comes the question of approximation. Okay, how close I can approximate to A. For example, see the role model example we should understand. 1 by n goes to 0. So 0 is there here. 1 is there. Look at all the elements. 1 by 2, 1 by 3. It goes like this. Never it touches 0 and all. Okay, people have vague ideas, or somehow it will go to 0. No, going and all, no. It's a notation. What do I mean by that? I mean that this 1 by n sequence eventually gets close to 0. This 1 by n sequence is eventually close to 0. What do I mean by that? Then naturally the shopkeeper will ask me how close he will ask, right? So what is the answer? Arbitrarily close. That means what? You give me any arbitrarily close. You give me any epsilon. Draw picture and understand. Let's draw picture and understand. Okay. Let's keep geometry so that line comes as a line. Okay. So you give me, it could be as small as I like. It could be, epsilon could be even 1 by 10 power 25. So far 9 nanotechnology, only 9 can be measured practically. But still, doesn't matter. You keep whatever epsilon. Mathematics is much more. Tomorrow somebody can come and say, I know 10 power 64 approximation. Doesn't matter. You give me any positive number. It is that close. That's what I want to. Epsilon comes only to say this idea. Okay, 1 by n is close to 0 means it gets arbitrarily close. That's it. You can give an epsilon. Then what will happen? See, 1 by this sequence is going like this. Okay, something like this. Now I will be able to find a stage, say 1 by n. After eventually close. After this, all the terms will be there inside this. For all n greater than or equal to n, this 1 by n will belong to this. This is very, very important. Okay, right. That's the idea. So AN converges to A means the sequence gets arbitrary, because please do not have a vague idea. Most of the people do have a vague idea. So general, how do I explain? Sequence is something like this. Seeing geometrically is very important. It is arranged like natural numbers. Now what I am trying to say, there is a stage n, right? This is called a stage, whatever the index set is there. Okay. After this stage, all the terms will be close to the pre-chosen epsilon. Okay, I can pre-assign the closeness first. Okay, therefore the definition says for every epsilon positive, there is a stage after which all the terms are epsilon close. That's the meaning. Okay, in terms of modulus, most of the people write, and it's very useful also, but this geometric point should not be left out. Okay, this is for manipulation. You can understand by a lot of examples. Okay, for example, if I want to prove AN converges to A, BN converges to B, if I assume these two, and assume if I want to prove AN plus BN converges to A plus B, then I want modulus. This is not that better. Okay, but if I want to prove sandwich lemma or something, this is better. Okay, geometry is better. Okay, fine. This is regarding convergence. Okay, now, yeah, you can see how things are, as I said in logic, you can see how it has been written. Given epsilon, there is a stage after which all the terms are inside this box, inside this interval, A minus epsilon, comma, A plus epsilon. Yeah. Finally, this is going to be an open ball. See, if for other people who have already done topology of convergence still, okay, if I have metric space, this is going to be simply replaced by metric. For topological space, this is going to be replaced by open sets containing that point. That's it. So base understanding is in R. Then later you can generalize to so many things, whatever I want. So that's not a problem at all. Right. Now, the problem under the point is, now I am going to have functions. Okay, there are two variables now for uniform convergence. That's the point which I have to discuss. For example, I'll take, okay, I'll give you I am going to have sequence of functions now. Okay, f1, f2, f3, something like this. What are these f1s? These f1s are functions, say, from a subset A subset of R to R. Let's now understand this in the context of real numbers. Then generalizing to topological space is same, nothing in that. Okay, understanding in R is important. Okay, the domain is A. A could be even very well R. Okay, so I have sequence of functions. So each f1 of, so therefore what do I have? I have for each x in A, so given x in A, so I'm going to have a lot of numeric. For each x in A, I'm going to have this following numerical sequence. Okay, F2, we call this as numerical sequence. This is function sequence. This AN, whatever I discussed, is a numerical sequence. Okay, so this is a sequence I have. Okay, now what do I want to say? For one example, let's give. Okay, let's talk of an example first. Okay, suppose if I define, see, I have to define for each n what is my f1 of x. Now I'll take A equal to R and define f1 from A to R by f1 of x equal to, let's keep it as x by n. Okay, so let's understand what is my sequence of functions. So what is f1? Yeah, so how does the thing look like? Okay, let's write the sequence f1 of x. What is f1 of x? f1 of x is x by 1. What is f2 of x? X by 2. f3 of x is x by 3. This I'm going to have. But x is not see, for each x in A, if A is given to be equal to R, so for each x in R, I have this sequence. Okay, I have a lot. Yeah. So that's the thing you have to understand. So for each x, I'm going to have a numerical sequence. Okay. Now I ask this question. Let's draw. First understand. See, whenever function is there, you can draw picture. Okay. Let's draw pictures, right? First function is f1 is what? X by 1. So let's try to draw that. Okay. Yeah. That is y equal to, oh my God. So I have to draw y equal to x graph, right? Yeah. Let's draw that near. Okay. Yeah. Yeah. Y line is not coming because my hands are moving. Okay. You assume. Okay. This is y equal to x line. Okay. Now x by 2. So where does it going to come? Slope is decreasing, right? So these are all the geometric points one has to understand. You assume. Okay, now it's moving. The line is moving. Okay, this is x by 3. But all of them are centered at, all the lines pass through origin. The way which I am drawing, okay, I am drawing in this vacuum board. It's not coming correctly for me. But all of you understand, okay, y equal to x, x by 2. So the lines get decreased. Okay, that's the geometry thing. Okay, this is. So for each x, you have x comma fx here, lying in this. That's in the graph of f1. This is the graph of f2. This is the graph of f3. Okay. Now I want to say fn converges to f pointwise on A. So f1s are functions from A to R given. For each n in n, f1s are functions from A to R. F is also a function from A to R. What do I mean by saying f1 converges to f pointwise on A? For each x in A, the sequence f1 of x converges to f of x or for each x in a, f1 of x converges to f of x. I should not, whenever convergence is there, we don't put this bracket. So the sequence f1 of x converges to f of x. In the notation, we don't put that. Okay, right. If and only f1 converges to f pointwise, if and this is my definition. Okay. Now I have to understand pictorially what do I mean. Right? Pictorially, what do I mean? Picture is very, very important to understand because uniform convergence and all is going to have pictorial idea. Okay, superseding this idea. So start with some x. And this is going to be my, this is going to be my x comma f1 of x. And this is graph, right? And the value is going to be here. Right? This is f1 of x. And that is ordered per x comma f1. And so that means actually it's something like draw the straight line. Okay. The straight line. Right. I have to draw fast so that it puts a line. Okay. Now I'll get all these. Wherever it hits, you go back and get this. Right? This is the range thing. Okay. So I'll get a sequence like this. Now from the picture, it's very clear. No, you can see where it gets close. See, these things are getting close to 0. Right? So that's what I expect and I should prove. Okay. That's about pointwise convergence. Let's do that. Let's prove this. Okay. That's very simple. So fix. So I got to see what basic idea one has to understand is there are two things. If you see f1 of x, there are two things. One is x in a. There are two variables now. One is x and other is n. That's what you got to understand. X is in a, n is there. N in n. Okay. Right. Before uniform convergence, let us prove pointwise convergence. Okay. That's important to talk of uniform convergence. Okay. So now how do I prove f1 of x? So fix. In fact, better take a. Fix x. Fix a in a. Now I want to prove claim. f1 of a, sequence f1 of a converges to f at a. What is f at a? Define f. F at a is 0. I know that. Already we saw in the picture. Okay. Let f from a to r be defined as a is r only now. F of x equal to 0. For all x, it's 0. So now I want to prove that. Now let's write, see what it is. It is a by n. That's it. Yeah, minus 0. Right? This I have to estimate. I want to make it less than epsilon. This also is important. Please understand. So how do I do that? A modulus of just a by n. That is mod a by n. Okay. N is positive. I can take it outside. Okay. Now a is fixed. I have to vary n. That's what we are doing here. Fix a. A is fixed. Now I have to vary n. I have to make it less than epsilon, right? I have to give a stage now. After which all the terms will be less than. So I have to give a stage for the sequence, this numerical sequence. Now my sequence is this a by 2, a by 3. I want to say this sequence converges to 0. Okay. Right. Now you give me, so how does this sequence go? Whatever may be my modulus, see, surely it is going to come. This 1 by n is going to make it go close to 0. That's what is happening in the picture also. Yeah. So this can be made less than. Yeah, mod a will be always there. I want to take, See, it is enough if I find a n such that mod a by n less than epsilon. Because the future n's are n is greater than or equal to n. That's what I'm going to say. Take n greater than or equal to n. Then 1 by n is less than or equal to 1 by n. 1 by n is less than or equal to 1 by capital N. So it is enough if I find an n such that mod a by n less than epsilon because of decreasing sequence nature. So how do I find Archimedean property? Okay, now by Archimedean property, what is Archimedean property? N is not, the set of natural numbers is not bounded above. Okay, therefore, really what I want to find is, you take n there, bring epsilon here. I want to say there is a natural number, there exists a natural number n in n such that n greater than mod a by epsilon, and that is possible. This is a epsilon is positive, therefore this is a real number. Okay, this is a real number. Set of natural numbers is not bounded above. That means given this real number, there is a natural number greater than that. Okay, Right. Then epsilon is positive, inequality won't change. I can go cross multiply and all. I have already done cross multiplication. Okay. Yeah. So therefore, that's all. Therefore, by Archimedean property, there exists n. Therefore, for all n greater than or equal to n, this comes like this. Okay, done. Okay, I have proved pointwise convergence. Okay, let's take one more example and understand. Okay, let's do, yeah, let's take a very nice thing. Let me draw the picture and then write down what it is. Okay, let's draw the picture. Okay, what I have in my mind. Okay, till, see, for me, till this thing, I don't mind. Okay, what I'm going to do is, I'm going to take 1 by n. Yeah, what I'm going to define is, after 1 by n, I'm going to have 1. Okay, keep 1 here. After 1 by n, all the values are 1. Okay, for fn. Okay, before that, I want a, yeah, I don't want to, let's keep this. Wherever picture is coming, we'll keep. Okay, we'll not have, yeah. So this is my 1 by n. At 1 by n, and I'll tell you what is this value. This value is 1. Okay, so, and this is my function. My function, I'll draw in green color, yellow color. Okay, this is my function. Okay, then goes like this. Yeah, one can do like this. These things one has to understand. Okay, now how do I define? So for at the end, I have told what is happening. So how do I define this function? Okay, how do I define? So define fn of x equal to, see, if x is, we know, if x is less than or equal to 0, my function value is going to be 0. Okay. If 0 less than x, actually what I'm defining is continuing. You can put 0 also here. It doesn't matter. For x between x and 1 by n, I want this line. And whenever x is greater than 1 by n, I want 1. Correct? Okay. For all x greater than 1 by n, I'm going to have 1. But how do I write this? What is this? Okay, this is nothing but, yeah, how to write this function? This is the point 0, comma 0, and this is the point 1 by n, comma 1. So now equation of the line passing through 2 points. Okay, that you can write down the expression. I'm not writing, you can write it down. Equation of the line passing through y minus. So what is the equation of line passing through? Y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1, and y equal to x is going to be the function for us. So you can substitute and write it down. Okay, that's the function fn of x. Now let's understand where does this pointwise converge. If x less than or equal to 0, I have to draw, right? For each n, now I have to draw. So let's draw. So what is this for x equal to 1? The function will be something like this, right? And n is 1. So till 1, I'll have this. Okay. And then I'll have. Okay. Then what will be my f2? F2, let's draw in different color. Okay. So what will be my f2? Till this, it will be there. And at 1 by 2, the value is going to be this. Okay. At 1 by 2, it will be 1. And then after that, it will go. Right. Then 1 by 3. Like that, you draw through some other color. See, all these things are required for understanding. Okay. So some other color you draw. So till 1 by 3, it's going to come. Okay. And then it goes. So this is the function graph. Right? So does it converge pointwise? Yeah. Yes. So if I take, you look at each of the picture for x. So what is my f of x? For each x, where does it converge? That's what I have to understand. So I'll define my f of x to be equal to, very easy point what I can find is, if x less than or equal to 0, this value is going to be 0, right? Because everything is a constant sequence here, 0. Okay. Yeah. And what I understand is, if x is greater than 1, then it is always 1. Then it is always 1. Okay. Is that right? If x greater than 1, it is always 1. That I understand. How about the points in between? So that I have to understand. Then only I can prove where it converges. Okay. So I want to just say like this. Okay. If x is greater than 0, I want to say f converges to this. f1s converge to this. Okay. Let's see what I'm doing is correct or wrong. Okay. So pointwise converge. So let's fix again. Let A belong to R. Okay. If A is same thing. If A is less than or equal to 0, then f1 of A equal to 0, and f1 of A is 0. Therefore, which is equal to f of A. Therefore, it's a constant sequence. Therefore, f1 of A converges to f of A. Okay. It's a constant sequence. Convergence is there. Okay. Now, I'll take x positive, A positive. Let case 1. This is case 1, right? Yeah. So case 1, if I have written. Now here, if A is positive, then I look like this. I want to, this is here is where we should understand. Okay. A is now positive. If A is greater than 1, no problem at all. Okay. Function value is 1 at all. But let's assume A is in between 0 and 1 for the time being, but actually that's not required. So what all I have to do? If I find an n such that 1 by n is less than A, as I have done for the previous case, then let's see what happens. That is possible by Archimedean property. So by Archimedean property, there exists n in n such that 1 by n is less than A. 1 by n is less than A. Therefore, same idea. Okay, by Archimedean property. Now, so what will happen for Fn at A? What will happen for Fn at A? Fn at A. Now see the definition. That's where I have to see the definition. Okay. Yeah. If x is greater than 1 by n, okay, now A is greater than 1 by n, the value is 1. Since A is greater than 1 by n, the value is 1. F1 at A is 1. Okay. Now, yeah, let's understand what will happen for all n greater. Let n be greater than or equal to. Given n greater than or equal to n. Given n greater than or equal to n. So what will happen? 1 by n will be less than or equal to 1 by n. And this is, so therefore what do I have? 1 by n is also strictly less than A. Therefore, what is f1 of A? f1 of A is again 1. So what happens is, therefore, for all n greater than or equal to n, f1 at A is 1. So therefore, even though there was a piecewise property here, it's coming and all, what we feel is this function, you can avoid, that's what, this thing, I'll take a 1 by n, okay, and I'll push the point x here. That's what is happening here. You should understand what's happening. Okay, for any point A, there is a 1 by n. That helps me. There is a 1 by capital N which is less than A. Any positive point. Therefore, this sequence of function converge to this. Okay, so very shrewd student will note what is happening. Okay, what is happening? Because my function is continuous, sequence of function is continuous, but my limit function, this I call it as a limit function, where f1 converges to f, that becomes discontinuous in pointwise convergence. Okay, and one more example. Okay, all of you can do that and see f1 of x is x power n. This is a standard example given in most of the textbooks, but this should be given at later stage, having understood all this sort of example. Okay, here what happens, let's understand. Here let's understand what happens. Again, draw picture. Let's give the limit on our own. So f1 of x is x. Then f2 of x is x squared. f3 of x is x cubed. Okay, but you should see where I can draw the picture. How does x cubed will come? See, between 0 and 1, you can see here also the curve is. See, between 0 and 1, x cubed graph will be still. Then above that, it will increase. Okay, I'm not drawing exact picture, but you can see. Why? Because of monotonicity. When x is positive, okay, if x is positive and x is less than 1, then x squared is less than x. Inequality won't change. Okay, so that's why the graph is here. And if x is greater than 1, then x squared is greater than x. Therefore, the graph goes above. Okay, all these things are happening. Okay, right. But what is the pointwise limit? All of you know, right? If it is greater than 2 and all, this power increases. Okay. Also, I can discuss from R to R. Here also for negative. Let's now take only positive. We'll concentrate only positive part. Okay, non-negative part. 0, infinity to R. So my set A is this. Okay, because we will make some conclusion. Okay, yeah, about that. Let's define. But the problem is, I can define this function, but limit function will not be there, because if I take 2, f1 at 2 is what? 2 power n. I know 2 power n is not convergent, because see, every convergent sequence has to be bounded. 2 power n is not a bounded sequence. Okay, it goes. But again, I can prove. See, here the proof comes by Archimedean property. Intuitively, you can feel the numbers are go on increasing. Yeah, exponential, right? 2 power n now, right? So it's not going to go. So the essential domain what I'm going to have is close 0, 1. Okay. 1 also it's defined. Okay. Right. So what will happen now? In fact, negative side if you include, you are going to have, yeah, -1 is problem. -1 whole power n won't converge. Therefore, you are going to cut till -1. Open interval -1. That's all. That's the domain of pointwise convergence. And where does it converges? For x equal to 1, it will converge to 1. For other, let's now write limit function. 1 if x equal to 1. If x less than 1, guess. I already said it's dying down, right? Graph is dying down. So if I draw a vertical line, you can see if I draw the points here, it goes to 0. Therefore, 0. So that's the limit function. That's how one has to guess. Okay, right. So now, how do I prove that? So f1 converges to f pointwise on. See, now our a got decreased. You should understand what is a. A is close 0, 1. Yeah, for 1 the proof is okay. If x equal to 1, constant sequence. Done. Okay, I'm not writing it. If 0 less than x less than 1, then what do I have? f1 of x is what? Yeah, let's fix a. We are fixing a. If you keep x, people always have x is a variable. A means they don't think as a variable. That's why for my student, we write actually. Okay, fix a in R. Fix a in 0, 1. Close 0, 1. If a equal to 1, then done. Okay, now take a to be, or a 0 also it's done, but it's okay. Okay, 0, constant sequence. A equal to 0, 1, constant sequence, therefore done. So keep a to be strictly in between 1. So therefore what happens? I have a power n. Now I want to ask this question. Where do a power n converge? I want to say a power n converges to 0. Okay. Yeah. Now power is coming on the top, no? How do I prove that? This is purely for students. In fact, it's very, very useful. If a is less than 1, I want to say a power n goes to 0. How do I prove that? Okay, I prove because power is on the top. So n is on the top. How do I apply Archimedean property now? Okay, So there I do this trick. A is less than 1. Therefore 1 by A is greater than 1. Okay, that's the idea. So 1 by A is greater than 1. I'll keep 1 by A to be some 1 plus H. Okay, so therefore 1 by A power n is going to be 1 plus H. Yeah, 1 plus H whole power n. 1 by A is 1 plus H. Therefore 1 by A power, okay, I'll write that so that you will not have a problem. So this is greater than NH. Okay, binomial theorem. 1 plus n, all the terms are positive. In fact, here also approximation sense come. I'll take only the term which I want. Okay, here I'll take NH. It's greater than NH. Okay, so now I want to prove, yeah. So what is A? Yeah, that's it. Now what is A power n? A power n is less than 1 by NH. Yeah, either use Archimedean property or you use sandwich lemma. This is bounded by A power n is bounded by 0. This goes to 0. Yeah, both of them go to 0. 1 by NH as a C. 1 by H is a positive term. Keep it as C. It is a C by N sequence. This goes to 0. This goes to 0. Therefore, this goes to 0. Okay, this goes to 0. That's it. That's the proof. Right. Now let's talk of uniform convergence. What do I mean by uniform? In fact, so many things are there. Let's talk of uniform convergence. So first we understood, right? What is pointwise convergence? F1 functions from sequence from A to R. From A to R is given. F from A to R is given. A to R is given. Now we said F1 converges to F pointwise on A. If I'll write it clearly, if for every epsilon positive, in fact I have to say first we'll say for each A in A, F1 of A converges to F of A. Okay, that's the idea. I can expand this for every A in A, for every epsilon positive. Yeah, there exists n in n such that for all n greater than or equal to n, yeah, modulus of F1 of A minus F of A less than epsilon. That's there. Okay, right. 3 brackets. Now I want to say F1 converges to F uniformly. On A, if for every epsilon positive, there exists n in n such that for every A in A, I'll take n later. And for, here I should, for every A in A and for every n in n, as for every n greater than or equal to n, okay, modulus of F1 of A minus F of A. In fact, we will not keep A now. We will vary X so that you understand better. F1 of X minus F of X is less than epsilon. Okay. So what we are telling? There is a common n which works for all X. That means after the stage, modulus of F1 of X minus F of X less than epsilon. Okay, let's understand this definition by picture. Okay, so what does this definition say? Okay, let's now keep F equal to 0. Okay, so for simplicity's sake, so I'll draw the function F. Now F is just this line, x-axis, right? Okay, now what should I do? Okay, I'll draw F1. Okay, let's take our first example. Our first example is this, right? F1 is this, F2 is this, okay, F3 is this, it goes on and on. So now what should I do? Okay, there should be a capital Fn, that's what it says. In particular, it should happen, no? In particular, modulus of F1 of X minus F of X is less than epsilon. Okay, keep even epsilon equal to 1, okay, or half or whatever you want. Let's keep this epsilon line and draw. See, this is, if you change it to inequality, you are going to get f of x plus epsilon, comma, f of f1 of x, f of x minus epsilon. Okay, so if you draw 0 plus epsilon, sorry, I have written the other way around, minus epsilon plus epsilon. So if you draw everything is 0 here only, f is 0. So minus epsilon plus epsilon. And if you take epsilon equal to 1, everything is going to be, or let's draw epsilon strip itself. If you assume this to be epsilon, our strip epsilon is going to be like this, right? 0 plus epsilon and 0 minus epsilon. Okay, right. There is a jump. Why did it jump? Okay, let's draw that. Okay, assume it is symmetric and the lines are same. Okay, because the, or let's do this. Okay, we'll rub this. Now what should happen? All the, see, what it should happen is, for all x f1, that means graph of f1 should completely lie within the band. That's what it says. So I should have. Will that happen? Definitely it will not happen. Because we know, right? It is going to, for whatever, even for very close, very large n, it's going to be like this. Slope is going to be very close to 0, right? But still there will be a, here also, for large point it will go out of this line. Okay, so what uniform, see, we have put only, there is a common n which should work for all x. That's where uniformity comes. One common n which works for all x. That's what I have demanded. But in picture the demanding is like that. Okay, yeah, so that's a problem. So will I have it? If I have a equal to r, then there is a problem. It won't have, I will not have uniform convergence. How do I prove that now? Let's do one by one. Okay, let's take the first example. Okay, what is our first example? f1 of x equal to x by n. F of x, that's what in picture I have explained. So we want to see, whenever we want, we will have a notation. Okay, f1 converges to f uniformly on a. That is what we write is f1 double arrow f notation. Okay, if and only if. This is the definition. Okay, so we will now prove f1 does not converge to f, double arrow f. Okay, yeah. So how do we prove? By contradiction. Same pictorial idea, we will replace that as a proof. Suppose f of x equal to 0. Suppose, yeah, fx 0 for all. Suppose f1 uniformly converges to a. Then we'll take some epsilon. Here we know anything we can take. For 1 also you can take. For epsilon equal to 1, there is a common n in n such that for all x in R, because now our A is R, f1 does not converge. A domain is very, very important. Okay, uniform for the domain. Okay, for all x in R and for all n greater than, yeah, I can put here, for all n greater than or equal to n, yeah, what should happen? Modulus of f1 of x minus f of x is less than 1. Okay, so in particular, modulus of capital f1 of x minus f of x is less than 1. Okay, this is keep it as equation number 1. I'm going to contradict. In particular, for all x in R, A is R now. Okay, so what is that we want now? Our f of x is 0. So what is that we are now trying to tell? X by n. For all x in R, see, I have fixed the n now. So I'm varying. For all x in R, modulus of x by n is less than 1, or mod x by n is less than 1. That's what I'm saying. That is, this yeah. So this is a wrong statement, right? Because why? Again, I can give a contrary. Choose some number. All of you know. Even most of the students say n plus 1. That's well and good. But If you are a bit careful, you can even choose n. N by n is 1. 1 less than 1 contradiction. Strictly less than 1 here. So same pictorial idea. Okay, that's what we are doing. Yeah, that large n itself we are taking. At that point, it should cut. All these things you can understand, but actually the ideas go further and further. Okay. Go for the second example. Second example also you can prove the function do not converge uniformly. You can't. You have to understand. Okay. Yeah. That you should understand. Then now comes. Yeah. What else we should understand? Yeah. So therefore, what happens is my x equal to choose x equal to n. Okay, that's what it happens. In fact, for the second one also you can see. Okay, one no. See, if I draw any graph, we will go to the graph and understand pictorial understanding. So one. See, limit function is here. It is 0. Okay. See, there itself you can understand. But even for this also uniform convergence won't be there. You go close to 1. Okay. Here, if I draw my epsilon strip, then any epsilon strip will come out of the one line. Okay. See, it's going out. Anything. Even if you go close to 1, because it has to come from 0, right? Okay. Here also uniform convergence is not there. Okay. All right. Okay. What are all the consequences of this? Okay. So let's work on this also. Well, let's take. Okay. So for if I take A equal to R, it's okay. But can I find a smaller set? Can I find, now I am going to change my question. Can I find A subset of R? Okay, some other set such that F1 converges to F uniformly for the same function. I'm not changing. F of x equal to x by n, F of x equal to 0. Okay, for this function, can I find a smaller set? Okay, possibly is it happening? That we have to go and understand. Now we have to estimate. Don't look for contradiction. We have to estimate. Okay, what is that I have to estimate? Simply f1 of x minus f of x. I'll simply estimate without any epsilon, nothing. I'm not bothered. Okay, this is x by n, that is 0. Okay, that is mod x by n. Okay, this also we know how to do. Now the question is, suppose if I put a constant bound here, okay, the good students will be able to say now. Suppose if I make it as L, okay, a constant L or capital M, something like that, okay, some bound by n, then I can do m by n, I can make less than epsilon by Archimedean property. So what it amounts to say? It amounts to say I should have for all x in A, mod x should be less than or equal to m. Okay. What does that say about A? That says this is precise definition of bounded set. If A is a bounded subset of R, then F1 converges to converges to F uniformly on that bounded set. Uniform means we should say the set uniformly on A. On whole R, we proved that it is not uniform convergence. Okay. Yeah. Okay. So this is how it goes. So we can do a lot of other examples. In fact, see in each of the third one is second one you can do. Third one I'll give a hint. Again in third one, so you can see the picture, no? See third one. Let's change and understand, because here Lot of confusions are there for students. Okay, we'll keep our domain only from home. We will even cut to 0. Okay. Okay, if I give now, what is my function? f1 of x is x power n, and my f of x is 0. Okay, I want to say it does not converge uniformly to 0. Why is that so? Let's look at the picture. Okay. See, actually, these pictures can be drawn. Okay, if you know, I'll give you some tool, open source tool, what is called as Sage Math. Okay, draw. Of course, if you have MATLAB, Mathematics, all those paid stuffs you can draw. I'm see, this Sage Math is a very free stuff. It's available in the web. It's available for both Windows and Linux. Go install this. In fact, I ask my students to draw a lot of pictures.
Sir, Srinivasan sir.
Yeah.
Sir, your camera is not on, sir.
Oh, I'm sorry. Okay.
Yeah. Okay.
Just to switch. Right.
Thank you, sir. Thank you.
Yeah, you can go and draw the pictures for this. Okay. So, in fact, it didn't occur to me. It is there in my machine, but I can't search now to find out. But anyway, how do the picture look like? The picture is going to look like this. Okay. So from 0 to 1, this is the interesting thing. Okay. 1 is there here. You draw the picture. Yeah. See, if I show the graph, be interesting. But anyway, drawing is also fun. So x square is going to come now. X cubed is going to be this. So the pictures, if you draw, okay, if I draw, I'll draw some things in the red line. Okay, you'll understand. Okay, it is going to go like this. See, come, bend and go. Okay, come, bend and go. Come, bend and go. Come, bend and go. See, usually students will think, sir, this one is the problem. So I cut. People will say, see, now I have all continuous function, right? X power n is continuous function. But still, see, the picture graph will be like this. It will coming, bending and go to 1. See, it will be like this. Yeah, it's going like this. Sharp, coming and going. So whatever 0 you give, definitely points are going to, how close you are going to give to 0, points are going to. See, the point is, it rapidly increases. Okay, here. And the proof is again same. Suppose it converges uniformly, take some epsilon, okay. Don't take epsilon equal to 1, it will be entire graph. Take epsilon equal to half, you can actually figure out which point actually gets out. Okay. And the trouble is because this is increasing. Okay. Now, how do I make this uniformly converge? How do I change? Okay. So, suppose if I define Gn of x equal to, I kill the behavior. Okay. How do I kill the behavior? X power n into 1 minus x. If I define like this, then the points at which x equal to 1 is going, they go fast. They go fast to 0. Okay. You look at this function, draw the graph, you will understand the convergence is uniform. The convergence is uniform. Okay. See, this is how one works. Okay. Let's talk just 5 minutes. Let's talk what is meant by uniform convergence in higher thing. Okay. Okay. Suppose if I have, see, all of you know, right? Set of all bounded functions. Those who have done, you know. So there is a set called B of x. Let's take R only. B of x, R. Okay. What is this? Set of all functions. Okay. F from x to R. Such that F is bounded. X is any set. Any set. Okay, not necessarily R and all. F is bounded. Bounded value, bounded functions. Okay, set of all bounded functions if you take, and if you put, if you define a norm F equal to LUB of modulus of f of x, because it's bounded, I can define this norm. LUB of modulus of f of x such that x varies in x. I can define because LUB will be there because its functions are bounded. Then this becomes a normed space P of x, R. Okay. Under this norm is called sup norm, LUB norm. Okay. Okay. That's why infinity symbol is a metric space. That one can prove. Okay, sir, what is the point you are saying this now? In this metric space, convergence is same as uniform convergence. F1 converges to F in Bx if and only if our old notion matches. F1 converges to F uniform. Okay. Of course, I talked from A subset. There actually I can keep anything. I'm bothered only about A could be any subset of X and I talk actually. So that's what is happening. The convergence is uniform. Okay. That's not hard to prove. One can easily see. Okay. So in B of X comma R, it is there. So if X is a compact metric space, or just take X to be closed a compact set. If X is a compact metric space or compact set, compact metric space, then every continuous function is bounded, right? So set of all continuous functions from a compact topological space also you can keep. If you want, you can make it in a very general statement. Then set of all continuous functions will be contained in this. Okay, therefore here also I can take sup now. Okay, here also the convergence, okay, norm convergence is same as uniform convergence. Okay, the norm convergence is same as uniform convergence. Yeah, I can do that in much more sequence space also in topology. See, all this have just a word uniform, but all of them have. Okay. And one more exercise also, right? Suppose if you have, in fact, how do you define uniform continuity? Same fashion. Okay. See, continuity is a local concept. Convergence is also a local concept. Continuity is a local concept. What do I mean by uniform continuity? Again, I have to be very careful and define. And most of the teachers' textbook always try to explain that this n is independent of. So you got to choose n independent of n. That we won't do, right? Do not say, do not compare this. Here, sir, here you see this a depends on n. Here, find an a independent of x. That is very tough to ask. How do I find n independent of x? Okay. Yeah. So do not say that. What we have to understand is I have a common n which works for all x. Similarly, for uniform continuity also same thing. Okay. Here one exercise is there is a connection between uniform continuity and uniform. Suppose if I define function like this, f1 of x equal to f of x plus 1 by n. Okay. Assume f is uniformly continuous. Okay, then I can prove this sequence f1 of x is f is uniformly continuous on a domain. Okay, on say a subset of R. Then this f1, yeah, converges uniformly. And uniform continuity is important. Likewise, uniform convergence is also important. Okay, later, in fact, topological thing is, see, I have all sequence spaces. Okay. Yeah. So same thing. I can. There is something called topology of uniform convergence. Okay. Topology with uniform convergence. Okay. There also I demand that only. So in the topology, convergence if and only if uniform convergence. Okay. That's how I will demand. Okay. Yeah. See, product topology, most of you who have studied product topology would recall. Okay, what is product topology? Convergence if and only if coordinate-wise convergence. That's how product topology is defined. That's why it is the smallest topology which makes projections continuous. Topology, uniform convergence means, in fact, it's usually an exercise in all standard textbooks of topology. Okay, right. I hope I have exceeded my time, right? Is that ma'am? Hello? So, do I have time? Should I stop now? Hello?
No, sir. No, sir. Time. Hello, sir.
Time is up, right?
Time is 11:39, sir.
Yeah. So, should I stop now?
You can stop by 11:45 or 11:50.
Okay. Yeah, fine. Fantastic. So, now let's do this first exercise. Okay. Yeah. So whatever we mentioned, F1 converges to F in B of X. So this, if and only if, we will prove F1 converges to F uniformly. Okay. This is important, and later people do. In fact, we use this to prove uniform convergence. We use maxima minima test. Okay. Let's understand this. Okay. Uniformly. So we'll prove that. Let F1 converge to F in Bx. That means what? Given epsilon positive, there is a stage n in n such that for all n greater than or equal to n, norm of subnorm, right? Subnorm of F1 minus F, is less than epsilon. Or in other words, some people will simply say this norm goes to 0. Both are same. Norm F1 minus F goes to 0. Right. Okay. This we have. Let's expand this. What do I mean by that? For all n greater than or equal to n, this particular n, this means LUB, right? LUB of x in x, modulus of F1 of x minus F of x is less than epsilon. Okay. LUB is upper. See, modulus of F1 of x minus F of x, LUB itself goes. That will be less than or equal to LUB, right? LUB, but that is given to be less than. Therefore, for each x, so for each x in x, I have this. Therefore, look at this. For every epsilon positive, there is n in n such that for all x in x and for all n greater than or equal to n, modulus of F1 of x minus F of x is less than epsilon. Okay, right. One way implication we proved. So we have to prove the other way implication. What is the other way implication? Suppose F1 converges to F uniformly. Now what we want to show? This converges, right? What we want to show? F1 converges to F in supra. See, then we have this, right? So therefore, then I'll keep this as star so that I need not rewrite. Okay, then star holds. Okay, star holds. But if I have this for every x, actually what I can say is, see, for each x in x, therefore, for each x in x, what do I have? Modulus of F1 of x minus F of x is less than epsilon. Therefore, what can I say about LUB? I want to talk of LUB. LUB of x in x, modulus of F1 of x minus F of x will be less than or equal to only epsilon. Okay. Correct, no? See, right. Suppose if I have, all of you understand this, right? See, each element strictly less than, see, in fact, we have this, right? Where do 1 minus 1 by n? Okay, 1 minus 1 by n is strictly less than n for each n in n. Okay, but what is LUB? LUB is 1. Okay, it is equal to 1. It could happen, that also. Okay, it can't go past 1, but less than. So how do I do this? This is where the trick. See, star is true for any, star holds for any epsilon. Therefore, don't start with epsilon, start with epsilon by 2. Okay. Therefore, for all x in x, this is. So, therefore, LUB is less than or equal to epsilon by 2. But this is strictly less than epsilon. You should not take F1 conversion. Let's start with, right? Let epsilon be positive. Don't start with the same epsilon. Start with whatever epsilon is given to you, divide epsilon by 2, you take. Okay. This epsilon by 2 will be less than. Therefore, LUB is strictly less than epsilon. Therefore, we have proved it. Okay. One more important concept in uniform convergence. Okay. This is very, very important. Maybe I should stop after saying this. So, when do I have uniform convergence? Suppose F1 converges to F pointwise. So, pointwise convergence is not. Whenever, see, also you should understand, whenever F1 converges to F uniformly, then F1 converges to F pointwise. Yeah, that's the thing. Uniform is much stronger. Okay, after a stage it asks for. Therefore, that you can prove, right? So, F1 converges to F pointwise, and F1s are, I'll say, uniformly bounded or Cauchy, uniformly Cauchy. Uniformly Cauchy. Then F1 double arrow F. Okay. On all these things are on a set. Okay. On A, we are assuming on A, F1 converges to F pointwise and they are uniformly Cauchy. Then F1 will converge to F. Okay. Why is that so? Right. We'll discuss. This is a very, very important thing. Okay. So let's do it. What do I mean by uniformly Cauchy? Again, uniformly Cauchy means that. Uniformly Cauchy means Cauchy in Supna. Okay. So given epsilon positive, what we have is uniformly Cauchy. Okay. There is a stage n in n such that this is the definition. For all n comma m greater than or equal to n and for all x in A, modulus of f1 of x minus f of x, fm of x is less than epsilon. Okay, it's uniformly Cauchy. This is what it is. Okay. Now let's fix an x in A and choose. Now what can I say about this? See, fix an x in A. So if I fix an x in A or A in A, now what do I know about the sequence f1 at okay. What do I know about yeah, exactly. What can I say about the sequence f1 of A? You can look at here. Modulus of f1 of A minus fm of A is less than epsilon. Okay, what does that say about the sequence f1 of A? F1 of A is Cauchy. Okay, so f1 of A is Cauchy in R. Real valued, no, we are doing only Cauchy in R. Therefore, every Cauchy sequence converge. Therefore, okay, that limit we are going to call it as. So, therefore, f1 of A converges. Therefore, f1 of A, the sequence f1 of A converges, say, to f of A. For each A, for each A, given A in A, this is going to happen. Say f of A. Therefore, we have a function f from A to R defined by f of x equal to L wherever this f, the sequence f1 of x converges. Where f1 of x converges. Okay. Or we'll call it, yeah, where f1 of x converges. Okay. That is what I am trying to say is it's the limit of f1 of x. See, most of the books will write like that, but that's the understanding. Okay. Now, what is that I have to say? Okay. Now, I am going to claim, yeah, pointwise it converges. Okay. Okay. To some function, I call that as f. Now, what is that I am going to claim? I am going to claim this f1 converges to f uniformly claim. So start with some epsilon. Let epsilon be positive. Okay. Now take the Cauchy stage for this. Okay. Now how do I do? Let's try to understand and do. I'm going to see. Let's keep this. We want to do like this. f1 of x minus f of x. We want to say, see, for given. So for all n greater than or equal to n and for each x, I will start an x here. We want to say this is less than epsilon. Okay. So how do I estimate this? f1 of x minus fm of x plus fm of x minus f of x. Now apply triangle inequality. Okay. Right. Now here comes the important understanding. Okay. How do I choose my n? I have already chosen. What is this n? Apply Cauchy stage to that. Okay. Since f1 is uniformly Cauchy, whatever the first stage, this n. Get n using star. Maybe you will write as some other, everything I am naming 1 using 1. Okay. Right. So Here I want to make it less than epsilon by 2 plus epsilon. That's our standard trick. Okay. So how do I choose my m? N I have already chosen. But how do I choose my m? M has also to be greater than or equal to n. Okay. Here I will use pointwise convergence. See, when I use pointwise convergence, depending on this x, this m will change. Doesn't matter. Okay. So how do I choose my n? Choose m equal to maximum of, okay, capital N, comma, I will have m of x. See, fm of x converges to f of x. No, for this x, there will be a stage. Since fm of x converges to f of x, for epsilon by 2, there is a stage. But that depends on x. If you change x, this will change. Okay, there is a stage. Call it as n. Call it as n1, but it depends on x. So for all n greater than or equal to n1, modulus of f1. So that I'll call it as x. It depends on x, but doesn't matter. Choose this m. Okay, then both of them will be less than epsilon by 2. This m depends on x. But here, note that here there is no m at all. Okay, so I have proved, given epsilon, I have found out a n independent of any. So here only x is. Okay, I want to prove, right? For each x I want to prove, no? So start with the n greater than or equal to n. Give me an x. For that x I will choose an m. Yeah, let that m be dependent on x. Doesn't matter. Choose an m. I have shown that this less than epsilon. Okay, again give me a different x. Yeah, the choice of m will be different, but doesn't matter. That I have proved to be less than epsilon. For each x, this m is going to change. Doesn't matter, I am proving this to be less than epsilon. But for common, here there is no m at all. Okay, for each n greater than or equal to n, this m is called Curry leaf. Okay, Curry leaf, which Professor Kumaresan, director of MTTS, have named this. So I am going to give as a reference his textbook. You can see what is Curry leaf, Karvapala. Okay, just like what is Karvapala? Usually people put it for flavor and then throw it out, right? Or catalyst of a scientist experiment. Okay, so it will come to add the reaction and then you can take it off also. Okay, this m comes like that. Okay, this is a Curry leaf. Yeah, so with this point I will stop my lecture. Okay, and as I said, I will give a reference. Yeah, start from basic. Yeah, so as I said, I will give that book first, Ajit Kumar and Kumaresan. A basic course in real analysis. In fact, entire functional analysis is going to depend. Lot of part of functional analysis, functional analysis completely this uniform convergence and all are so basic for that. Okay, then of course now it has become like a all over Indian textbook. Bartlett, it's a very good book. Bartlett and Sherbat, Introduction to Real Analysis. Introduction to Real Analysis. Yeah. Yeah, these are all two references. Of course, there are plenty you can see. There is one Torrance to textbook also. You can see interim series. Okay, apart from that, all of you know the regular textbooks, right? Apostle, Rudin and all. Okay, fine. So, yeah, with this I will stop my talk. I will stop my sharing, right?
Okay, sir. Thank you very much, sir, for your thought-provoking lecture. So, no questions. Okay. PG and Research Department of Mathematics, D.G.VAISHNAV College is conducting C4 Chase Crack Conquer CSER Net scheduled today from 6 p.m. to 8 p.m. and tomorrow from 11 p.m. to 1 p.m. In view of end semester examination, webinar series will resume in the month of January 2021. Information regarding this will be informed to all the participants through email. Feedback link will be posted shortly. Gratitude is the healthiest of all human emotions. I thank Almighty for showering blessings in making today's webinar a successful one. I express my sincere thanks to our Secretary Ashok Kumar Mundra and our Principal Captain Dr. S. Santosh Babu of D.G.VAISHNAV College for providing an excellent opportunity to conduct this national webinar on uniform convergence. I convey my heartfelt gratitude to Professor R. Venkatramanan, Head, PG and Research Department of Mathematics, for his constant support. A warm and sincere thanks to our resource person, Dr. P.S. Srinivasan, Assistant Professor, Department of Mathematics, Bharathasan University, Tiruchirappalli, for enlightening everyone with his lecture on uniform convergence. Thank you very much, sir. A special thanks to all the participants across the country for their enthusiastic participation. Thank you, one and all. Jai Hind.